we've looked at constant, linear, and quadratic polynomial functions. So that's degree 0, 1, and 2. Degree 0 and 1 were very similar to each other because the graphs were straight lines. Degree 0, the straight lines were horizontal. Degree 1, they were at a slant. Degree 2, quadratic, we had parabolas, so these kind of U-shapes or upside down U-shapes. And we looked at the quadratic situation in rather a lot of detail because the algebra was quite rich. Taking a kind of quadratic equation or quadratic function, so ax squared plus bx plus c in standard form, that's standard form where a, b, and c are all constant, we can manipulate it algebraically to put it in vertex form or perhaps factorize it, and that gives us an awful lot of information about the function. So the general case is what I want to look at now. So let's look at higher degree polynomial functions. Higher degree polynomial functions. So we've studied the algebra of polynomials quite a bit now. So we did it in the algebra section of the course, not really thinking about things as functions, just thinking about the expression given by the polynomial. So thought of as a function, a polynomial function in general is a function of the form f of x is equal to, so I'm going to write a general polynomial and I'm going to write it in the format I did then. So a0 plus a1x plus a2x squared plus ... all the way up to an x to the n. So this is a general polynomial function where the output is just a polynomial expression in x. This is a general polynomial function. So a0, a1, a2, all the way up to an, those are all constants. They're called the coefficients. They're all real numbers. The variable is the x pretty clearly. N is a non-negative whole number. It could be 0, in which case you just have a constant function. So yes, n is called the degree, where an, assuming a sub n is not equal to 0. That is a possibility here. And ordinarily when we write down polynomials, if any of the coefficients are 0, we just don't bother including them because it would be 0 times something which is 0, so it doesn't affect the sum at all. Okay, so we want to kind of understand what these functions look like in general. And here's the first thing to be aware of. So fact, graphs. So let's focus on their graphs really. Graphs of higher degree polynomial functions have more varied behavior than degree 0, 1, and 2. Have more varied behavior than the bottom cases. So constant, which is just horizontal lines when you do the graphs. Linear, so non-negative, non-zero slope graphs, or straight lines. And then quadratic, of course, parabolas, which we've looked at in a lot of detail. So they've got a lot more varied behavior. We are not going to have a theory as complete as for these bottom cases because the algebra is more complicated. In particular, there's no version really of completing the square for a general polynomial, and it's just because the algebra, as I've said, is more difficult. Unsurprisingly, there are more terms of higher degrees. You can't put a general polynomial expression in a vertex form in general. So this is kind of problematic. It means all sorts of like nasty things later on. It means, for example, finding zeros of polynomials is very difficult. This is one of these classic subjects that we've been thinking about for thousands of years. The Greeks thought about finding zeros of general polynomials. And for quadratic, constant, linear, and constant's not very interesting because it's just a horizontal line. But for linears and quadratics, we have, well, linear is very simple because it's just a straight line that crosses at one point, very easy algebra to find a zero. Quadratic, I suppose we could put it in vertex form, solve, that's just a quadratic formula, but higher degree things become much more hairy. So this means we can't possibly come up with a completely general theory in the same way that we did for these lower cases. But there are certain kind of key properties that are worth kind of talking about. So I'm going to go through, I think, 6 pretty interesting examples to begin with to show you the different behavior that might turn up. So some of these we'll have seen before, some of them we won't. Let's go for it. So examples. It's good to have kind of a collection of kind of very standard polynomials in your mind, so you really know what they look like. So we've already looked at things like, well, quadratics, x squared, we know that very well. Let's now think about, let's do a cubic, shall we? So I'm going to do 6 guys, I think. So let me... So forgive me while I just set this up. I'm going to have a few of these. I want to go through some interesting cases that are going to be indicative of the general case, or the general picture that I'll do my best to describe, even though it's quite complicated. Okay, so let's do one to begin with. Let's take, what do we do? Let's take y is equal to x cubed, shall we? So on the positive side, so for positive values, it looks very similar to x squared, although it's kind of steeper if you want, at least eventually. So it looks kind of like a normal parabola. Just because something looks a bit like a parabola doesn't mean it's a parabola. You need to understand this. A parabola is, by definition, the graph of a quadratic equation. So if you're the graph of a non-quadratic equation, whatever, it doesn't need to be a polynomial. If you look like a parabola, it doesn't mean you are, right? It just means you have a similar format. It's something to understand. Now the difference here between x squared is the moment I become negative, the cube of a negative is negative. So what ends up happening is, in fact, I'm going to cheat a little bit because we already know this. This is an odd function. So it means it has rotational symmetry. So, a few things. First off, it's got 1, 0. Of course it does, right? It's got 1, 0 at x is equal to 0. So the x and the y-intercept coincide here. So maybe that's worth writing down. So 1, 0. All right, what else? Well, I can also see it's increasing, right? You can see as overall, as you move from left to right, it's going up, so it's increasing. Very nice. Well, as I said, it's odd. Of course, if I take minus x and cube it, that's minus of x cubed. And finally, it's visibly unbounded. The range is all real numbers. We're going to kind of catalog this in a little bit, but I just want to get some examples out there. So it's unbounded. Unbounded above and below. So those are just some things I can immediately see. All right, let's do another one. So let's do one that's a bit more interesting. Let's do y is equal to, let's do 1 minus x cubed. Now this one's interesting from several perspectives. First is, we could technically get the graph of this starting from this by some elementary transformations. For example, I could take minus x cubed first, which would be a reflection in the y-axis. Then I would add 1 to it, which would raise it, a reflection in the x-axis. And then I would raise it up by 1, translating up by 1 by adding 1 to it. So it's going to look very similar, but it's going to be kind of negatives or reflected in the x-axis and then raised up. So it'll look like this, roughly speaking. There. And then on the other side, it's not an odd function, but it has the same kind of story to it. Whoa. So it's like this. So it's not odd because it doesn't have rotational symmetry around the origin. So this is a bit of a subtle thing. If I was to take this point here and rotate it 180 degrees short, it would be the same, but that's not what odd is. Odd is you're rotating around the origin, and that's not going to work. If I rotate around this point, it wouldn't stay the same. Okay, so a little bit of a subtle issue there. So can I spot anything? Well, first of all, yes, it's the same deal here. It's got 1, 0. So the same property. So 1 x-intercept. It's decreasing, isn't it? That's a bit different than before. Again, it's unbounded. It's unbounded. Anything else? It's neither odd nor even. Neither odd nor even. Just some things we can see immediately from the graph. Let's do another one. A bit more difficult. So let's do y is equal to x cubed minus x, shall we? And just to say something about this, we can factor this. This is equal to x factored out by x squared minus 1. We've done this factoring before, actually, in the early algebraic videos, but it's x plus 1, x minus 1. Okay, so it factors out like that. So that tells me it's going to have 3 zeros, 1 at 0, 1 at minus 1, and 1 at 1. And also you can notice it's an odd function because all the powers are odd. It's 3 and it's 3 and it's 1 at the powers. So remember, this is a shortcut that we can do only with polynomials to determine if something is an odd or an even function. A polynomial is an even function if and only if all of the exponents are even. This is kind of where the terminology comes from. And a polynomial is odd if and only if all the exponents are odd. Okay, so what this means is it actually looks like the following. So this one's kind of interesting. So it's going to go up, it's going to cross, it's going to be a minus 1, then it's going to come down to here. And then it's going to be odd. So that means it's going to basically be this thing rotated around. So let me show you. So I'll do a little shortcut as usual. It's going to look like this. So that's going to be the shape of this graph. So now, first of all, we've got this point here, this point here, and this point here. So this is minus 1 here. This is 0 here, of course, and this is 1. So these correspond to these 3 factors. So in this case, we've got a cubic again. So we've got a degree 3 polynomial, but something interesting's happened. Not like the above examples, we're getting 3 roots. Oh, sorry, 3 zeros. When you say root of a polynomial, often that means a 0 of a polynomial, not to be confused with things like square roots, cube roots. They're kind of related, but it's a little bit more general when it comes down to it. So if I do say the root of a polynomial, it means a 0 of a polynomial. So this is 3 zeros. So interesting new behavior. Still unbounded, because the range is everything, we can see that. It's odd in this case. Interesting. And it's much more complicated when it comes to increasing or decreasing. So overall, it's not increasing or decreasing. No, right? Because sometimes it's going up, sometimes it's going down. It depends what interval you're on, really. So, for example, if you were talking about the function past this point in the positive direction, then it's increasing. But if you're thinking about the function between these 2 points, then it's decreasing. So what I'll say is it's kind of sometimes increasing, sometimes decreasing. It depends on what interval you're looking at. Sometimes increasing. Have I written bitten off too much here? Is it too small a space? Sometimes increasing, sometimes decreasing. So it's much more subtle. Interesting, right? So it behaves a little bit more like a quadratic in the sense that a quadratic, we definitely know because of the parabola shape, sometimes increasing, sometimes decreasing. It depends which side of the vertex you're on. But here it's a lot more complicated, right? So good example. Next example. So I'm just trying to show you lots of the different behaviors that can turn up. We'll do another cubic. So let's do the cubic y is equal to x cubed plus x squared. Feels very similar, but it is actually quite different. So this is equal to, we can factor out the x squared plus 1. So have I gone mad? I have. I can factor out the x squared, can't I? It's even stronger. Now this one's interesting because what are the zeros of that? We don't have 3 of them, we've only got 2 of them. It's x is equal to 0 and x is equal to minus 1. So this actually looks like the following, and this isn't completely obvious at all. This looks like this basic shape. And I'll kind of talk about why it's this shape in a little bit. But it has to look something like this because I know it's got only 2 zeros. These are the 2 points where it crosses. Minus 1, and 0. So again, this is interesting now because it's got 2 zeros as opposed to 3 or 1. So these are all cubic equations, right? All cubic equations, but I've got potentially 1 0, potentially 2 zeros, potentially 3 zeros. And I suppose we saw this kind of behavior a little bit with quadratics, because quadratics, the parabola, either it doesn't cross the x-axis, so there are no zeros in the real numbers, which would correspond to, I suppose, if we're going to do things algebraically, to b squared minus 4ac is strictly negative, so we can't take a square root in the quadratic formula, or the quadratic crosses at 2 positions. Or it could cross at 1, I suppose, or just touch at 1, so it just intersects at the bottom at the vertex or the top. So we've got lots of different behavior here. So same deal with the cubic. What else? Well, it's unbounded again. The range seems to be all real numbers. That's kind of a constant among all of these cases. It's neither odd nor even. Neither odd nor even. And again, it's sometimes increasing and sometimes decreasing, isn't it? So it's kind of quite complicated. Right, so already from the cubic case, we know it's going to be a pretty varied situation. Let's do some degree 4. These are often called quartic equations, but that's a bit less standard. So let's do just the most obvious one. Let's do y is equal to x to the 4. Now this one's interesting because it's extremely similar to x squared, but we're doing a power 4. So here, when you graph it, it's actually really, really similar looking, but there are certain key differences. The main one being it's kind of flatter to start off with, because if you're less than 1, when you multiply by yourself 4 times, you're smaller. But then it kind of climbs more steeply once it gets past 1. So it kind of goes out like this, and then it kind of goes up like that. So it does look kind of like a parabola, but it's kind of flatter at the bottom and then steeper afterwards. Not that that's terribly important. Just something to be aware of. So this is kind of, get back to my statement before, sure, it has the same kind of form as a parabola, but it isn't a parabola because it's not literally the graph of a quadratic equation. So here, 1, 0, obviously it's 0. So just 1, 0. Anything else? Well, this now is kind of different. It's, again, sometimes increasing, sometimes decreasing, just like what we saw with the 2 previous examples. Is it bounded? No, it's not. Not overall, because it's getting positive. It's unbounded in the positive direction. It can get as high as it wants if you're kind of going up here and up here. Just like a quadratic. However, it's bounded below, which is new, right? Because the cubic equations, none of them were bounded at all. It's not bounded above, but it's bounded below. And in this case, it's most definitely even. If I feed minus x into x to the 4, 4 is an even number. So minus 1 to the power 4 is just 1, no effect. So that means it's got reflective symmetry when I reflect across the y-axis. Okay, a nice way to visualize it. All right, let me give you one that's quite a bit more interesting. So this one I'm going to give it in totally factored format rather than have it multiplied out. Imagine if I have y is equal to, let's do the following. What should we do? Okay, so let's do minus x minus 1, x minus 2. Am I going to be able to fit this? I'm going to have to shrink this down a bit, sorry. So we'll do y is equal to minus x minus 1. We'll do x minus 2, x plus 1, and then we'll do x plus 3. So you know if you were to multiply this out, you would get a quartic equation of degree 4, because when you multiply, you've got 4 x's that would turn up. You also have a negative at the front, and what that's going to do is something similar to a quadratic equation in the sense that it's going to turn it upside down. So what we can also see is that this has to have, I think, 4 zeros, doesn't it, right? Corresponding to zeros of each of these pieces. So that's going to be at 1, 2, minus 1, and minus 3. So the actual shape of this is the following. I'll do my best here. It's not so easy. Oh my goodness. It's going to be something like this, probably. So this is interesting. This now feels quite different than what happens with a quadratic, for example, because it's got this wiggle at the top. This now is more like a combination of the quadratic, if you want, and the cubic, right? There's this kind of behavior along with the kind of parabola type behavior we're seeing for the degree 4 case. So it's interesting. So now what do I have? Well, these 3 positions are minus 3. I think it's minus 1, isn't it? It's 1 and then it's 2. So it's a little bit lopsided. So I don't want to give you the impression it's like a parabola, which is perfectly neat, right? It's kind of, it could be a bit of a, one peak could be higher than the other, shall we say. So this guy now has 4 zeros. Okay, interesting. It's bounded above now, I suppose. It's definitely neither odd nor even because, well, you can see that from, it can't possibly be odd because it's degree 4. And it can't possibly be even because if I reflect it in the y-axis, it can't match because of the 2 and the minus 3 not matching up. So neither odd nor even. Let's just, rather than write it again, let's just steal it. And of course, much more complicated, increasing, decreasing behavior. So it's all over the place. It kind of wobbles back and forth. So it's sometimes increasing, sometimes decreasing. Okay, so to conclude, let's take a look at all of these together. Shall we? Can we fit them all? Sorry, it's a little bit small. But to conclude, even for degree 3 and degree 4, it's pretty varied behavior. I think we can definitely agree with each other that it's madness to attempt to give a complete description of all possible scenarios. Even degree 3, all sorts of different things seem to be happening. But there is something of a pattern going on. For degree 3, you're unbounded. So you're kind of going off towards positive infinity or negative infinity, if you want to say that kind of loose terminology in either direction. And you potentially have this kind of single kink in the middle. You may not. Like the first 2 examples, you have this single kink, but you don't seem to have more. For degree 4, you have the same behavior in both directions. You're either getting massive positive or massive negative, and you kind of have kind of some sort of maybe a kink in the middle, but not really a kink, kind of a double kink. So one more wobble, I think is what you want to call it, than an actual cubic equation, for example. So you can probably guess what happens with the degree 5. For degree 5, so I'm just going to write this quickly. I'm going to erase it because I'm going to talk a bit more coherently. But for degree 5, you can probably guess. For degree 5, what would happen is, in general, okay, you would look like kind of, you could go up. So you'd behave a bit like the cubic equation, right? So you'd have a scenario where you would, on both sides, maybe look something like this. But then you could potentially have some wobbles in between. So the wobbles would be 1, 2. So that's kind of like a degree 4, but then you could turn again. So I think that could happen with degree 5, right? So I don't know how many turns it is. 1 turn, 2 turn, 3 turn, 4 turn, right? And degree 6 would be the same thing, but you could go up to 5 turns, which would kind of turn you around. So that basic story holds in general. So let me describe this carefully. So let's do the general form. So this is me talking a bit blue sky, because I can't possibly be really accurate about this, but I'll be as accurate as I can be. So let's talk about the general form. General form of the graph of, let's say, a degree n polynomial function. And let's just settle on the notation just to make sure we're completely confident here. I think maybe we should, I think this is correct, we should just settle on quadratic and above, because some of the lower terms may be confusing. Degree 1 and 0 is straight lines, it's very straightforward. But when I'm talking about one of these polynomials, I'm thinking about this, just as I talked about at the beginning. And an is non-zero, so it is degree n. And we'll have n is greater than or equal to 2. So we're quadratic and above when I'm talking about this. Otherwise, what I'm going to say is slightly off, I think. Maybe that's not correct. Maybe I could include the linear, but let's see at the end if I think it's sensible to include it. So we definitely know now there's going to be a split between the even and the odd case. So let's break it into 2. N even. So let's get this correct. N an even number. There's a difference between an even function and an even number. I'm talking about the number now. So n an odd number. What else do I know? Well, I know, just thinking about quadratic equations, that the sign of kind of the front term, my an if you want, is going to make a difference. If, for example, your leading term a in the usual standard form for a quadratic function is positive, you're a u, and if it's negative, it's upside down. So again, I'm going to have to break into 2 cases, rather annoyingly, depending if an is positive or negative. So we'll do an greater than 0, we'll do an less than 0. And we'll do the same thing over here. Okay, so let's try and do this. Even an greater than 0, it's going to be a U shape, but with some wobbles at the bottom. So it's going to look like something like this. So dot, dot, dot. And then it's going to kind of wobble. I don't know exactly how many wobbles. Like this. This is going to be the shape. And here, well, it's got to be between 1 and n minus 1 turns, if you want to think about it like that. So I'm just trying to work out how many times you're turning. So it's got to turn at least once. So between 1 and n minus 1 turns. And in fact, if you think about it, it's going to have to be an odd number of turns, because we need to go back up. So if it was 2 turns, So if I went down 1 turn, 2 turn, oh no, right? That's not going to fit the pattern. So actually it's got to be an odd number of turns. And notice it's between 1 and n minus 1. So it doesn't have to be n minus 1. It's going to be some number between the two. Let's just scroll up a sec. Like this, for example. Whoa. This, for example. This is only 1 turn. Whereas this guy is 1, 2, 3 turns. So it doesn't have to be kind of the n minus 1. It's somewhere between the two. So that's if we're positive. If we're negative, well, it's the same thing but upside down. So it looks like this. That kind of business. It doesn't need to be symmetric either. It doesn't have to have any kind of symmetry. It could be kind of pretty wonky. The things could be at different heights. But it's the same basic story. So again, this guy. It's between 1 and n minus 1 turns. So that's the basic shape. So we're not being too precise here, but I just want to give us a feel for this. So now basically, if we do the odd case, it's the same story, but you're going to have, I think, an even number of turns, which means you're going to flip direction. So if you are odd, you're going to look at the same thing, right? If you're positive, you're going to come in from negative values. But then what's going to happen is you're going to have an even number of turns, actually. And what's going to happen is you're going to turn and end up like this. That's going to be the shape. So this guy is now between, let's see, between 0, sorry, between 0 and n minus 1 turns. Same story as before. And now the number of turns has to be even. You can't be an odd number of turns because you'd have to turn back around and be going back down as you move from left to right, which can't happen. So it's 0 to n minus 1 turns. And finally, the other guy, it's exactly the same story, but kind of flipped. So you would end up with something like this guy. So you'd come in from the positive values this time. And do your wobbling like that. So that's the basic shape in this situation. And it's totally identical, right? You'd have, again, between, what is it? Between 0 and n minus 1 turns. So let's just do a little sanity check. Could we have included n is equal to 1 here? If n is equal to 1, you'd have odd. You'd be a straight line. Would a straight line fit with it? Well, I suppose a straight line would fit with it because you'd have 0 turns. It's a totally straight line. N is equal to 0 wouldn't fit though, I think, because if n is 0, you're even. And the way I've set this up, you have to have at least 1 turn, which wouldn't make sense for the 0 case because it's just completely flat. So let's just avoid those cases, right? That are so simple. We could, I suppose, do n is 1, but let's just not bother, right? Because it's straight. So neat, right? This is the basic story. It's a good thing to know. And it is going to tell us some useful stuff about the general format of polynomials. So it will tell us some things, as we're going to see. But it's not going to be anything like as precise as what we saw with things like quadratic equations or constant or linear functions.